Okay, so literally for just a couple minutes, I'm going to talk about partial derivatives. So far, we've thought of derivatives as kind of these methods to calculate rates of change. And that's exactly what partial derivatives are, luckily. But with normal derivatives, so that's called first order derivatives, first order ordinary derivatives, sorry. Say we have some curve like this, right? This is our f of x, say, and this is our x, right? So if we get some change in x, we're going to get a change in f of x. So for example, if you kind of look at this small triangle created, actually I'm going to make it a bit nicer. If we kind of look at this example here, I'm going to move this a bit over. So if this line here was instantaneously small, or if it was infinitely small, sorry, an instantaneous slope, we would get a change in x and a change in y, and our derivative, so f prime of x, says that the slope of this line will be delta y by delta x as the change in x approaches 0. And eventually we can just say this is dy by dx, where the d kind of represents an insanely small rate of change. It's infinitely small kind of change in x. And that's just the ratio of how fast the y changes compared to how fast the x changes. But notice how this is only when one variable is changing. So if the x moves to the right in this example here, well then we're going to move up the function because it's concave up, right? Its second derivative is positive. If we were to move to the left, right, say in this example, our function value would get lower, same kind of idea, but what if we were in 3 dimensions? So let's say we kind of had a new axis that we declared. Let's say this was, so this is now f of x, y, and then this would be the y-axis. We kind of rotate that y down. Now it's going to be a bit different because we're going to have a 3-dimensional function where multiple things are changing. So maybe it's kind of going in the x direction and it's going kind of up to the y, kind of into the page and then out. It's kind of hard to draw, but it's kind of doing all this weird stuff, which you'll see with how heat's distributed and lots of things in nature where things are changing in multiple ways, or yeah, more ways than one. It happens more often than not, right? So partial derivatives just say if you have a function, let's say this function that I drew, some random function, f of x, y is equal to, let's say it's x squared y plus x minus 2. Okay, we can't just say what's the derivative of this because we want to know like what the derivative with respect to y is, because the x can be changing and the y can be changing. And if the y isn't changing, well then that's not a partial derivative. Or the partial derivative with respect to y is just 0, right? So if we say what's the derivative of this, we have to declare, well, with respect to what? So we use these curly d's. We say df, our function f, by d, let's say x. This means how is the function changing with respect to x? So for every kind of little nudge to the right in the x direction, what's the function value changing by? And notice how this isn't the height anymore, because we also have this y dimension and the f direction. It's not just the height, it's the function value. So luckily we take the derivative the same way. This is just a polynomial, so if we're taking it with respect to x, we say, okay, well then y must be constant. We're going to say it's not moving. So if we're only moving in the x direction, y is a constant. So we're going to use the power rule, right? If y is constant, we're taking the derivative of x squared. This is going to be 2xy, right? Plus, well, the derivative of x is 1, and then minus 2, the derivative of that with respect to x is 0, so it's just 2xy minus 1. So this is kind of a new relation for if you want some way to determine how the f value is changing for every change in x, you plug your actual x value and your actual y value in, double it, and add 1. That's going to give you kind of how fast this function value is changing. I guess I can kind of use the analogy of height, but that's not really what it is. It's just a function value because you can rotate the axis so that the y is the height, the x is the height. It's not the best kind of way to think about it, but I guess because I'm not like really able to draw it in 3 dimensions, that's a decent way to think about it. Okay, same kind of idea for different types of functions like exponential, logarithmic, that kind of thing. So I'm going to talk about how to compute partial derivatives. I'm going to get into really more applied, more involved examples, maybe using some tables as well, but this is just kind of what partial derivatives are. Converting from the natural df by dx, that was a horrible d, into the curly d's, right? And we can also say, well, what's the derivative with respect to y? Well, that's where per some change in y, how's the function of f of xy changing? And we can use this for partial differential equations as well, a ton of stuff. So I'm excited to get into it with you guys, and I'll see you there.